Okay, so for part 1 of 3-2 notes here, we talk a little bit more about dynamics, which again, dynamics are equilibriums for objects in motion. So we'll see some dynamics pop up. We will, however, see some more static equilibrium as well, as our first few examples may illustrate. But static equilibrium, again, when objects are at rest, dynamic equilibrium when objects are moving with a constant velocity, because they are in equilibrium, so my net force is 0. And they are moving therefore in a straight line with a constant velocity. The one thing that I do want to mention real quick, right, we know equilibrium means the net force is 0. The very important conclusion that comes from that is, if I know my net force is 0, then I know the sum of all of my horizontal components has to be 0, and I know the sum of all of my vertical components has to be 0 as well, right? So it is very, very important that we realize that those two, because they're completely independent of each other, those two are also true if I know that the net force is 0 because it's in equilibrium. Okay, so make sure we're comfortable working with that relationship. But anyway, we'll see some examples, and really most of this section is just revisiting some examples, hopefully most of which aren't too bad to work through. So if you're going through this section, if you want to try them and then just check and see if you got the right answers with my solutions, that is perfectly fine as well. Okay, so I'll give you guys a chance, if you haven't read through, obviously read through this question. And probably the trickiest part about this question is just getting a feel for what all the measurements are here. And obviously you can see off to the side, I've gone ahead and broken up my diagram. So it tells me that both of those tensions are pulling with a force of 60 newtons. So I've got 60 newtons for each of those forces. And then they do give me the angles involved. Again, I know the picture gets pretty complex, complicated here, but if you kind of read through the directions, they say that this tendon is pulling 10 degrees above the femur, so this angle in here is 10 degrees, and then the tendon that connects down to the lower bone is pulling at 70 degrees below. So if you actually kind of look at the diagram, and I'll maybe try to make this as clear as I can on that diagram, but the femur is pretty much just horizontal. It's pretty much my x-axis here. This tendon is pulling 10 degrees above it, and then this patella tendon is 70 degrees below it. Okay, so again, probably the trickiest part about this question is just getting a feel for what it's actually looking like. But the diagram that I have off on the right over here is showing what's happening. So then if it's in equilibrium, if it's not moving, right, then what force does the femur have to push? Well, they're showing me that force there, right? That's that red force that they've got on the diagram. So I'll show that over here with that red force as well. This is what I'm trying to find. Well, again, this is really just an equilibrium problem. Once I've taken the time to kind of set this up, hopefully this approach is pretty easy, right? All I'm going to do is I'm going to figure out what are my components for each of these forces, and then make sure that the red force over here balances out those components from the two pink forces that I have here, right? So again, going through this, I'm just going to find what are the components of this force that's pulling 10 degrees above the angle, what are the components of this force down here that's pulling 70 degrees below the horizontal, and then I'm going to balance out the net forces from those two, right? Because I know it's in equilibrium, and therefore the total net force is 0. So taking that one at a time here, right? I've got that going off at 60, I've got that going therefore to the left and going upward, right? So I've got my hypotenuse, I've got my angle of 10 degrees. It's easy enough to find those two components. So when I calculate that, I get about negative 59.1 for the horizontal component, and I get about a positive 10.4 for the vertical component, right? So nothing too crazy there, just a little simple right triangle trig. Doing the same thing then for the 70 degrees below the horizontal. That one goes partially to the left and partially down. So here this is 60, here this is 70 degrees, and again finding those two components, I'm going to define both of these as negative since they're going to the left and down. So about negative 20.5 to the left and about negative 56.4 newtons going down, right? So then if I'm thinking about this, the big conclusion is, again, my net force, the sum of all of my forces, is 0. And because the sum of all of the forces is 0, I know then that the horizontal components need to total up to be 0, and the vertical components from all three forces need to total up to be 0. So if I want to find the force of that red patella as it's pushing back out, right, I'm just going to find the resultants that I need for these two forces. So if the sum of the total horizontal forces is 0, and right now I have two horizontal forces that are negative 59.1 and negative 20.5, then obviously my third force, so I'll call this Fx3 for the x component of my third force, but that obviously then needs to balance out these two. So that third component ends up being about 79.6, and notice it is a positive 79.6 newtons, right? So nothing too crazy. The exact same type of rationale then for my vertical components. Again, I know all of my vertical components need to add up to be 0. I have one that is positive 10.4 because it was going up, so that is a positive number. I have one that is negative 56.4. And then I have my third component, right, the y component of my third force, right? And so again, that needs to balance out. It needs to compensate for the difference between those two. So solving this relatively easy equation, right, anyone can do it. So you guys definitely can. I end up getting about 46 newtons. And again, it needs to be a positive 46 newtons, which is consistent, right? Both of these numbers end up being positive. That actually is consistent with the picture that they were suggesting. I know that this force now goes over 79.6, and I know that it goes up about 46, I guess, was what we worked with, right? So it goes over 79.6 and it goes up 46. So if I want to find the actual force of that, I just need to do a simple Pythagorean theorem, right? So doing the Pythagorean theorem, we end up getting that third force, that force from the patella pushing outward, would end up being about 91.9 newtons. So again, about 92 is maybe what I'll call that, about 92 newtons. And the angle, because it does ask me for the force, I should always try to find the angle. And even going back, I can't remember what force, no, it just says force, but we do always want the angle because force is a vector measurement. So finding the angle just using a little bit of trig, it ends up being about a 30-degree angle. It ends up being about a 30-degree angle. So anyway, hopefully nothing too crazy with this, right? Nothing too chaotic going on there, but definitely something good to be comfortable solving. So anyway, we've got that question. Again, hopefully you tried that on your own, then just maybe checked your answers here. Getting the diagram set up was probably the trickiest part. So then the next example, again example 2 here, feel free to read through this and try this on your own first. My bet is you guys probably would do fine on it. If you do obviously want to check though, I will go ahead and work it through as well just to make sure you guys all feel pretty comfortable with this. But anyway, they tell me the weight of the car is 15,000 newtons, and then they tell me for part A the maximum tension that the rope that's towing this car up the hill can withstand is 6,000 newtons. They ask me, using poor grammar, I ask you, will the rope break under constant velocity? Well, the big concept there, the big reason that I threw that in, just to make sure again we're thinking about it, if it's constant velocity, right, if it's a constant velocity, that tells me very importantly that the net force is 0. And so if the net force is 0, and for part A I am going to go ahead and neglect friction, right, they tell me to neglect friction, then I'm just considering what forces are acting on that, right? I know that any forces have to be equal and opposite because the net force is 0. So I have my force of gravity pulling down the ramp, I have the tension in the cable pulling the truck up the ramp, and then I have my normal force, right? Those are actually the only 3 forces that act on it for part A, right? I have my normal force perpendicular to the surface, I have my tension pulling the car up the ramp, up the incline, and then I have my force of gravity pulling down. Right? Those are the only 3 actual forces acting. Now I do have to consider though for this problem, right, I always want to break the force of gravity up into its components. And make sure you are careful about how you break that triangle up, right? The force of gravity is the hypotenuse. This vertical component is equal and opposite to the normal force, right, unless there's something pulling off of the ramp or pushing into the ramp. But in this case, that force is equal to the normal force. And then this component here, right, so if this is my angle of theta, which they told me the angle involved was 20 degrees, right, then I know that this angle here would be 20 degrees as well just by doing a little basic geometry. So I've got my hypotenuse of 15,000. I can pretty easily find my 2 components, which I'll do in just a moment. But more importantly, right, this sine component of the force of gravity in this particular problem, because it's moving at a constant velocity, that sine component of gravity would be what's equal and opposite to tension. So if I want to figure out if this truck can pull the car up the incline here at a constant velocity without snapping the tension, I just need to see what the force of gravity that the tension needs to match is. So the only thing I'm going to find then is, again, just my force of gravity times the sine of theta. So when I calculate that, when I do Fg sine theta, so again, my force of gravity is 15,000 newtons because they gave me that number to work with, and my angle is 20 degrees because, again, they gave me that number to work with. So 15,000 times 20 ends up being about 5,130. There's a decimal as well, but I'm going to go ahead and round it off to 3 sig figs. So then what that tells me is this force pulling down the ramp would be less than the maximum tension, right? So in this particular instance, with this incline and this force of gravity, tension would only need to match that 5,130 newtons, and therefore, yes, it would be able to pull it up without snapping. So my answer for part A, yes, it can pull it up, no big deal, right? It will not break the rope. For part B, what is the maximum coefficient of friction that the surface of the road could have to pull a car up the slope at a constant velocity without braking? So the idea here is, well, if I focus again on that car, so now I've got the tension pulling up, I've got my force of gravity pulling down, and now I'm throwing in friction, right? I'm saying that, yes, there is some friction involved. Okay, so for part B, I've got friction. Well, I still know this number is 5130, right? That number doesn't change depending on if friction is here or not. And I still know the maximum tension would be 6,000 newtons, right? So the reason it's helpful to think about that is if it's moving at a constant velocity, then friction would be the exact difference between these two numbers, right? So my friction would end up being 6,000 minus the 5130, so the maximum frictional force that I could withstand would be 870 newtons, right? So I've got that 870 newtons, which is good. So again, if they just ask me for the frictional force, I've got it. But in this case, they don't just ask me for the frictional force. They ask me what's the coefficient of friction. Well, to find the coefficient of kinetic friction, I need to take my coefficient times the normal force and set it equal to 870. Well, to find the normal force, right, it's just what we would normally do, no pun intended, right? If I'm looking for the normal force, again, it's the cosine component of my force due to gravity because the object is not accelerating into or out of the incline there. So my normal force, if I want to find that, again, it's just the cosine component of gravity. So normal force equals Fg times cosine of theta. Again, they gave me those two measurements to work with. So 15,000 times cosine of 20. So my normal force then ends up being about 1,530. Nope, I'm sorry, that's my mass. I read the wrong number there. So that normal force ends up being 14,000, basically 100. It ends up being like 95 and change. Again, I'm going to go ahead and round that off though, just to keep it simple. So there's my normal force. I've got my frictional force, my normal force, finding coefficient of friction. Not too bad from here, right? So my coefficient times the normal force of 14,100. And obviously, just looking at the difference in these numbers, it ends up being a pretty small coefficient of friction. Okay, so if that road had any more than 0.06, really, or somewhere around that, 0.06, 0.07, but if it had any more of a coefficient of kinetic friction than that, then we would not be able to tow this truck up the hill at a constant speed. So anyway, got that part for part B. I do realize here that I forgot to answer the rest of part A. Part A said if the rope will not break under the tension, what is the maximum acceleration that the car could be towed with? Well, if I know that it won't break, right, the maximum acceleration would come from the difference, right, because the net force would then be my tension, my maximum tension minus the force of gravity, that sine component, right? So again, my net force would actually end up being that same 870 that I used for friction. So if I want to find my acceleration, I just take 870 and set it equal to mass times acceleration. Well, that does require me to find the mass by simply dividing 15,000 by 9.8. So when I do that, that's where I was getting that number of 1530 from before. So that's where I was getting my number of 1530. So then plugging that in times the acceleration and solving for the acceleration, the maximum acceleration that we could have up the hill without any friction would be 0.57 meters per second squared, right? So anyway,